I'm AI Joe on the tweets, and I'm the principal organizer of the meetup. It's really awesome of all of you to take some time out from your busy workday and be here today, so thank you very, very much for that. And I just also want to acknowledge that some of you will have found the meetup today for the first time, perhaps through Techweek, perhaps as a personal invitation from IBM. And I'm really thrilled to have you here because we're always wanting to extend our reach into new companies and players. And some of you who are new here today are going to be part of organizations who are doing really cool things with AI, and we're really keen to have you guys really actively involved in the meetup. So if you are working on something you're passionate about with AI, please consider coming along to either do a talk or to do a lightning talk. Or if you have someone that you work with who inspires you in the area of AI, please have a chat with them and put them in touch with us. It's really easy to find us. You can Google NZ AI Meetup or Google AI Joe. It's not hard to find it. And you can get in touch on LinkedIn or Twitter or meetup.com itself. And please do sign up on meetup.com if you haven't done that directly. And you'll find out about our future events, where we often have international speakers, and you'll have an opportunity to help you keep up with all the developments in the AI space and hear from some people who are really at the top of their game. And we're only going to be doing bigger and better things in the future. Now, just to give you a breakdown of what's going on today. We will have, first of all, I just want to acknowledge and thank IBM for providing this amazing venue. They're our key sponsor, and after the show today, they will be also feeding you all and getting you all drunk. So let's give IBM a big round of applause for that. And in a moment, we're going to be able to welcome up Jeremy Nilmeier. Have I pronounced that correctly? Yes. He has a huge amount of experience in this space, and he's an IBM developer advocate and a data scientist at the open source data and AI technologies. And also we'll have a QA after that, and then we'll have the food. But before that, please allow me to invite up IBM's Eunice O to have a word with you all.
Hi everyone, I echo what AI Joe said, welcome, and very happy to have you here today. So first things first, health and safety. In the event of a fire, please follow the IBMers out the door, down the stairs, and we'll assemble in the quadrangle below. As for toilets, if you haven't looked for it already, it's through these sliding doors to the right of the reception. Now that's out of the way. My name is Eunice, like AI Joe said, and I am a strategy and analytics consultant here at IBM. Now at IBM, I'm very excited, and IBM's also always very excited to be part of these sessions, because especially since we are focusing on TensorFlow today, because it's a very good reflection of our long-standing commitment to the open source approach. And we've actually, with TensorFlow in particular, we've embedded it into our product. So for example, I'm sure a lot of you would have heard about Watson. So Watson exports into TensorFlow. Now hardware also uses TensorFlow. We are also very cognizant of the good that technology can do in the world today. And so given the number of people here in this room who have developer skills, I really couldn't resist the opportunity to encourage all of you, if you haven't already, to find out more about the Call for Code this year. So that is a worldwide developer competition that IBM runs, and it's aimed at developing technology solutions for natural disaster preparedness, response, and recovery. And so last year, over 100,000 developers took part from 156 countries. And wouldn't it be cool if this year, a team from New Zealand won? So there's going to be more information about that in your follow-up packs. So do have a look. Now, refocusing back on the star of our session, Jeremy. He's actually just come from Think, which is our flagship client event that just wrapped up in Sydney. And this year we had a Code at Think event. and Jeremy led the TensorFlow stream that was very well received. So we are very lucky to have him here over today. He flew across the ditch to share what he did with them here with us right now. So welcome, Jeremy.
All right, well, thank you so much for having me. Anybody hear me okay? This is my first time in Australia, first time in New Zealand, so it's just an absolutely beautiful country, and thank you so much for bringing me out. Today I just wanted to talk a little bit about TensorFlow 2.0, and let's see, oh yeah, we got a plugin. I can see it just fine over here, so, all right.
And it will be up on screens to your right as well.
Yeah. When I go to do demos, sometimes I'll forget to drop out of the PowerPoint presentation, and I'll be typing away over here, and the slides will still be up, so if that happens, give me a yell. So this is designed really to be an interactive session. So when I did this at Think at Sydney, it was a session that was completely interactive. So you know, we can stop, we can run code. If you want me to jump into the next section, or if you have questions, feel free to stop me. This is there's only a few slides that I really just, you know, where I'm just covering stuff. The rest of it is we're running through notebooks and things like that. So to that end, I was just curious, how many people are pretty comfortable coding in Python? Okay, how about how many people are familiar with Jupyter Notebooks? Okay, scikit-learn, Pandas, TensorFlow. Okay, good. All right, cool. And Apache Spark? Okay, that's right. Yeah, that's how I got started at IBM, working in Apache Spark projects. It's near and dear to my heart. Just a little bit about me. I am a data scientist, developer advocate. Started out at Spark Technology Center. That got rebranded into Code-A, and I'll talk a little bit about what Code-A is. My background is not necessarily traditional computer science, so I went on the kind of data scientist journey. I started out with a bachelor's in engineering, got a PhD in computational biophysics, so I spent a lot of time programming, but it was not a computer science degree. And did a lot of postdocs around the Bay Area of San Francisco. Gradually migrated into a boot camp called Insight Data Engineering. Do they have these kind of boot camp data science programs here in New Zealand? So around the Bay Area, they have these like kind of 6-week programs where if you're coming from a non-computer science background or some other background, it's like this really intense boot camp where they kind of retool your skill set to whatever the industry is looking for. So just curious to see what the community's like here around things like that. But so yeah, I just want to jump in and talk a little bit about IBM and their commitment to open source. And Eunice talked about this a little bit, but we were the founding members of the Apache project, the Linux Foundation. We were one of the original founding members of Linux, and now we just bought Red Hat for $34 billion. It's funny, it's a $34 billion company with no IP. It's kind of an amazing thing. So we've been committed to open source, and pretty much all of the major open source projects that are out there, IBM has a significant footprint in. So it's something that we're really proud of. Our particular group is completely open source. All we do is advocate for open source projects, contribute to the projects. The general idea is that a rising tide lifts all boats, so we want to make sure that the good open source projects get the traction that they need to get the adoption that they need, because once these things get going, there's really no better way to develop code. So the group that I belong to is the Center for Open Source Data and AI Technologies. It's a really tough name to remember, but it's just Code-A, and so this is French for coder and coded. And really our goal is just to promote open source projects. This was a relaunch of the Spark Technology Center. So originally, basically, we had the same mission around a project called the Apache Spark Project, which was one of the largest open source big data frameworks out there. I mean, it is now. And pretty much now it's a de facto standard, so our advocacy efforts really, we didn't need to invest as much into promoting that project because it was already kind of an established project. So we expanded our scope to include most of the AI frameworks. We also cover things like graph databases and some other open source projects. GPUs. Okay. Any other accelerated hardware people are using? TensorFlow Lite. Anybody using that? Or TensorFlow? Oh, wow, man, cool. TensorFlow.js. Anything like that? Okay, great. Okay, cool. So there are lots and lots of examples that we could go through in TensorFlow 1.x, but since 2.0 is coming out, we're focusing the examples today on TensorFlow 2.0, and really it's one of those things where we're really encouraging if you're writing code for the first time, go ahead and start in TensorFlow 2.0. It's currently in alpha, but it should be released here, GA, here pretty soon in the next few months. And it's worth it. Just there are just a few minor tweaks here and there to your code if you want to go from 1.x to 2, but may as well just write it in 2 at this point. It's going to be the standard. And then once it's right in 2.0, it should be the de facto standard for quite some time. So, so for those of you who are into the sort of differences here, we just want to cover it. So that we have this data API called tf.data now. It's a little bit. You'll see how I'll show you how it looks. It's a good way to kind of organize your data into batches when you're doing stochastic gradient descent. And we have tighter integration with Keras using tf.keras now, so you don't import the library separately. It just sort of comes bundled with tf. How many people are familiar with Keras? Okay, cool. Most of the examples that we're going to go through today are Keras. And it's getting to the point now where you're pretty much encouraged to use Keras over TensorFlow unless you really, really need to. And typically, if you're writing in TensorFlow, you're doing something that's probably on the research level and maybe not quite the application level. So it might be worth it to see how far you can get with Keras, and then you can drop it in TensorFlow if you need to. So they do have this thing. It's not really. It's kind of its own separate project, but a thing called TensorFlow Hub now, which is really easy to download. You can pull down models and do things like transfer learning and get pre-trained models. And it's just a nice repository. So it's starting to get to the point where we're trying to, okay, so we know that GitHub is we know that GitHub is the place to put your code, but where do we put models? And how do we store them? And what part do we store the whole model? Do we just store the architecture? Do we store the parameters? If we want to do transfer learning, do we just store a fraction of the model? All that stuff is starting to become a question. So TensorFlow Hub is starting to address that, and so you'll probably start to see other repositories like that where you can download neural networks. So now you can run and debug with eager execution, and then you can do this thing called tf.function where it does this thing called autograph, or constructs a computational graph. So how many people are familiar with the tf.session, session.run in TensorFlow? Okay, so all that stuff is finally not necessary anymore. You can just use this where it just runs as an eager execution.
Sorry to interrupt, Jeremy, but I just found historically with that microphone, if it's in your pocket, it tends to get the interference that you're hearing.
Oh, okay.
If you clip it on, if you've got a external pocket or belt.
I had it on my belt, but maybe it was running or doing some kind of crazy thing back there. I don't know. Let's try up here.
We've got some more batteries if you'd like.
Okay. All right. So, yeah. Let's see. We'll try doing this back here or something.
Sorry for all the buzzing.
Didn't realize it was me. I thought it was me.
But okay, I got it there. So now we can just do this eager execution. You don't have to speak to the context the way you used to have to. So it's definitely much more elegant. And this is really a function of the APIs that NVIDIA makes available to and some of the other hardware APIs. So this is definitely a lot more convenient. It's a lot more it's a lot more user-friendly, and you don't really notice it until you're writing TensorFlow code. The Keras stuff is usually pretty much you just build the model and then train the model. So they do have a much more elegant framework for distributing computations that wasn't there before. So how many people were familiar with Horovod? Horovod was came out of Uber. It was an MPI-based parallel framework that distributed calculations for TensorFlow at scale. This one now has the strategies for dealing with multiple GPUs, multiple CPUs, the whole gamut of arrangements for running distributed training. But we won't be able to come through examples today. I just haven't got the hardware set up quite yet for that, but I'll try to get the hardware going and have demos for you guys at some point. But definitely the libraries are there, and they're quite good. We can export to safe model. This is going to allow you to do things like TensorFlow serving, TensorFlow Lite, all of the ways that you want to serve this, particularly on these sort of edge devices. This is going to be the de facto standard. There's going to be a bit of a standards conundrum, I think, because there's another open data format that we also support called the ONNX, Open Neural Network Exchange format, which also is used by lots of frameworks. And so it's not clear what the standard is going to be at the end of the day, but certainly this is in the TensorFlow universe, this is going to be the standard that they're going to be using. So, and it's very good. It's very good for doing all the interchange stuff, and there's lots of scripts for converting back and forth to all these file formats. So I typically like to spend a little bit of time on just what a neural network is. I don't want to spend too much time. Just let me know if I'm talking too much about this. Hurry me along. If you have questions, stop me and ask them. But I like to at least give enough so that when you see this stuff, you kind of have a picture in your mind of what we're talking about. So how many people are familiar with what a neural network is? Okay, great. And so we'll just jump into it, and just so you guys have a picture in your mind. I guess I'll do it from here. So the idea here, and the reason I wrote it this way is because this is the way TensorFlow thinks about this, is you have a function, which is an operation that is carried out on this input data, which is this Z. And that function is the neuron. And that neuron is really just one of these functions. And actually, it could actually be a more complicated function. If you're familiar with something like a RNN, this function could actually be a very complicated neuron. But for most of the examples that we're talking about, it's just this simple one of these functions. Typically what you'll see for the performance reasons, a rectified linear unit is the one that you'll see most often. But so the idea is you take a whole bunch of features, which are a bunch of x's, you combine them using this x times w, which is just, and w is the weight vector applied to the feature vector, and then a bias term. Now in TensorFlow, this is actually an operation. That's why it gets its own special note. That's why it looks kind of funny. But normally it would just go directly into here. But if you were to actually do a graph, computation graph, in TensorFlow, it would assign this multiplication operation to its own graph. And so you carry it out, and then the outputs can go to either other neurons or as outputs. But that's sort of the picture in your mind of a single neuron. And then they're almost always arranged in layers. And by layer, that just means that you have a whole bunch of neurons here, and then you add a layer here, and then those are connected to those neurons, and usually what's called a dense layer. And the only reason we want to bring this up is that they're not arranged in a cobweb. They're not just, you can imagine these neurons can be connected in any way you can imagine. neurons can be connected to several layers across, or the whole notion of a layer could not even exist or anything like that. But for the purposes of understanding how the API works, it's almost always arranged in these layers. And it just turns out that this has been the set of good practices that everybody's adopted and understands how they work. And really, at the end of the day, these are just really very complicated functions that we're fitting to lots and lots of data. But it just turns out that we're defining these functions in the same way. We've sort of agreed that we're going to put them in layers, and they're going to have weights and biases and all that kind of stuff. So, so this is just a very simple neural network for identifying numbers. How many people have actually run an MNIST prediction? Okay, good. We do have a Hello World example that we can go through here, so you can see what it looks like in TF 2.0. But so what's happening here is you take the input image. This is 28 by 28 image. You take that image and you flatten it out, and then that's an input vector here. And excuse me, and then the input layer has 784 inputs, because that's what you get when you flatten it out. And then it just goes through a few hidden layers. As long as there's some internal layer, that's where we get the deep part of deep learning, right? There was a time in the field where a single layer with many, many neurons was thought to be the ideal architecture. Now we understand that having layers in the middle is what really makes the network performant. And so the output here is going to be a series of neurons, and in this case there are 10 neurons. And what I'd like to ask is, does everybody understand why there's 10 neurons in the output layer here?
10 classes.
Right, there's 10 classes, right? Okay, that's good. Just sanity check, make sure there's on the same. And right, so we've got 784 inputs, 10 outputs. So this is a classifier. So there are two different types of neural networks that you can construct in terms of the classic supervised learning field. One's a classifier, the other one, does anybody know? The other one?
Regressor?
Regressor, that's right, regressor. So, and you can have a multivariate regressor. You can have one, floating point number come out, or a series of, a whole set of floating point numbers come out. We do have a regression example. So now we're just gonna jump into this example notebook. So this is gonna get pretty interactive. I'm just gonna run through some of the code so you can see what it looks like in the notebooks. If you want to run these examples, go to this bit.ly link here. They're all there. And they are going to be in IPython notebook form. If you want to, so in order to run them, if you happen to have Jupyter up and running on your machine, on your local machine, they should work with, I think you're going to have to be a little bit careful about the pip install TensorFlow 2.0 part of the notebook. Some of it's commented out, some of it's not. But they should all run. And the other way you can do it if you don't have your environment set up is we have this a hosted environment called Watson Studio. Is that me? Was it?
I'm not sure where the interference is coming from. So.
I don't know.
Do you want to try this mic? You have to hold it, I'm afraid.
Might be the best approach. Let me try that. Maybe I can steal that one for Q&A. If someone does have a question, feel free to put your hand up anytime, as Jeremy is keen for an interactive session. And do allow me to give you the mic, so just for the sake of those watching this on video later, so they can hear your question.
Can you guys hear me okay? Okay.
It's very directional, so try and point it at your mouth rather than speaking over it.
Is that better? Yeah. Not quite as loud. Maybe that's part of the problem. I think the volume's pretty high on that one. Okay, so as long as everybody can hear me, I can do that. Actually, I can probably just talk. Thank you. So, okay, so yeah, I might need to talk because of typing and all that stuff start happening. So what you can do is go to our hosted environment. So we have a free version of Watson Studio that will run all of these examples, and because all of these examples, you don't even need a GPU to run them. So you can just you can download and run it on your laptop. But if you don't want to bother setting up all the TensorFlow stuff, you can run it from. So let's see. So what this does is it's a Jupyter notebook that has a kernel that's pointing to a kernel that's running on some server somewhere. So it's a Kubernetes-based system. So it just finds its virtual machine and spins it up, and then you can run remotely. So right now we don't have GPU accelerated instances, but by the time 2.0 comes out, when the hardened versions comes out, then we should have GPU accelerated versions of this running. But to learn the syntax, you don't really need to have all that GPU stuff, and just need to figure out how to do all this stuff. So I just wanted, okay, so this is a quick overview of some of the features of Keras. So we'll just run through some of this stuff here. Okay, so here's the pip install. Now this is going to be very interactive. I'm just going to be running this code. So if you have questions, what's happening, let me know, because really just going to get into the nitty gritty of what the API looks like, what the inputs and outputs looks like, and all that kind of stuff. So this is the pip install. So if you want to do TensorFlow-GPU, this is the version that you pull up. If you want to do TensorFlow, it's 2.0 alpha version. Then, so we'll just go ahead and make sure this is working. Of course it's not. And that's usually because you have to reinstall the TensorFlow alpha. So we'll go ahead and do that. And then in order to do that, let's see if we have to restart the kernel or, so then okay, so 2.0. So that's a thing to check, because if you're playing in this alpha space, you're going to be installing and uninstalling all the versions to get it to work. Particularly if you're doing the tensor board. Anybody using tensor board before? So I'll have an example. Tensor board will run in a notebook. It's not running in Studio yet, but it'll run on the Jupyter notebook. And you have to get the versions right for that one to work. So building a simple model here. So this is the sequential API. Everybody familiar with the sequential API? So yeah, you just basically you build it sequential, and you just add a layer and just pile it on. So yeah, that's why we spend a little bit of time saying, look, these things are connected with layers, they're in an orderly way, and this allows you to do that. So you can find the activation layer, you can find the output layer has the softmax activation. All the other ones, all the internal ones have value for the numerical properties.
So far, is there anything different for TensorFlow 1 versus what you've done here?
I can't remember if the sequential API looked the same in TensorFlow 1. I think that one is a little bit new, but most of this stuff is pretty similar. Yeah, definitely. I mean, it's not unfamiliar, right? I mean, all these. But I think the sequential one was before it was you had to define it as one model. That one with the appending was different. So there's some of the ways you can define. This is just a little tour of the syntax that you can use to define some of these layers here. Then, so this one here. I can't remember if categorical cross entropy was the one that was used in the earlier versions, but certainly it's the one that's preferred. I see this one used more than any of the other ones. And this whole thing about the metrics, this is the part that it gets tracked for if you want to plot anything with TensorFlow or anything like that during the training process. This is all tracked. Is everybody familiar with all of these terms here? Does everybody understand what an optimizer is and what it does in a neural network? Does everybody understand what the atom optimizer is? Versus stochastic gradient and all of that. So atom is definitely the one that's used most frequently, and or the SGD optimizer. So I guess the thing to remember about these optimizers is they take batches of data and then they run gradient descent on the batches of data. So the fact that the data, if you can organize the data in batches, it will run more efficiently. So that's part of the motivation behind the tf.data API. You'll see that they'll sort of arrange this data in batches that are a little bit more easy to get to. So here's some of the choices for the loss function. The mean squared error is used for what? Does anybody know?
Regression.
Regression. Yeah, regression is a better loss function for that, and then all the other ones are for the category predictions. So now once you create the model, then we compile the model, and then we just use this model summary, and then it's just so this is this is from the training docs here. So basically, we're just walking through the things that were thought to be important here. One, you can use this NumPy, which is something that you've been able to do for a long time in TensorFlow. So the data is just is now these NumPy arrays, and then you can train on that. Now you can, let's see, you can also do it with the validation data. So here's the datasets API. And so here is just, you can create these batches now. So this is a little bit more convenient for some of the model fitting. And this will become more and more important as you run the distributed calculations and all of that. So let's see, we'll go through some of the other things. Evaluate and predict. So evaluate's a pretty handy one. It will run on the entire data set and produce metrics that you specify. And then model predict. So these are just the model fit, model evaluate, and then model predict. Now this is new. This thing called the functional API. Is anybody familiar with this one? Yeah. So this is really will allow you to write classes for all of this. So you can do this thing called model subclassing, and now you can create an actual method, and then your model exists as a Python class. There could be cases where this is really useful if you're committed to a large code base and you really need to have a class that does this kind of thing. Then it's nice to have this available to you. But I've heard it recommended even by the TensorFlow developers to, hey, maybe if you can use Keras, just use the Keras API. It's a little cleaner. But it's definitely something that's available. So you've got this class equals my model, and create it that way. And then if you want to do other fancier stuff, you can do custom layers and all of that. Callbacks are the better way to understand callbacks is we'll come back to it later. Is just by seeing it by example. I didn't understand what a callback was. I still don't fully understand what a callback is, but once you see it in practice, it kind of makes sense. So then there's the save and the restore of the model. These are nice examples here. So you create the model. The model is something that has architecture, and it also has this optimizer, all the loss and all the metrics and all that kind of stuff. But then there's another separate component to it, which is the weights, right? So if you remember the neural network, we had the function was had x times w plus b. Well, the weights are the w part of that equation, right? And the b's are there too. All the other stuff, the arrangement of the neurons and all the layers and all that kind of stuff, that just sits in something called model. But then the weights are something that kind of exists independently of it, and that kind of makes sense because if you have a model that's going to be, let's say you're retraining this model on data that's changing every night or something like that, you definitely don't want to have to create a new model. You just want to update the weights for that model. So this is a sort of standard way of doing it, is you create the model, and then that model has a method called save weights. And then you can load the weights and do all that kind of stuff. So you can imagine you have lots of versions of the weights on the same model, basically. So same thing. The standard format's pretty much the same as H5 format. And this has been around too, this JSON conversion string. So this is the configuration part only that you want to save. And this one is actually, you can save the model as an H5 file, but these models aren't massive, right? They don't take up gigabytes of data, so it's easy to save it as a JSON file. And there are other, for example, the Onyx file format. You can edit these things manually so that you can get good interoperability. So it's kind of nice to have this JSON format for this kind of stuff. And you can save it in YAML format too. I think we're going to get into that one. Okay, so here's the fresh model, and you just reload it from the JSON string, and then you convert it to YAML. Same kind of thing. And then recreate the model from YAML. So. Now I think this is new in the 2.0, is you just save the entire model. In TensorFlow there you would save the entire model as this thing called a PB, protobuf file, which is a frozen graph, sometimes they call it, and it has all the parameters and the model all in one file. That's what's happening here now, you just save it in this H5 format. So this is pretty handy as well. Again, things like the only reason I keep bringing up Onyx is we just gave a talk on this not too long ago. The Onyx format also has everything built into one file on the frozen graph. So it depends on what space you're in, whether you want to have that model and parameters in two different files thing happening or not. So that's that. Okay, so here's some stuff about the eager execution. We'll see some of that a little bit later. And then also the distribution part. So this is unfortunate because I do want to get this. This I think is going to be some of the more interesting stuff that you'll be able to do with this, is when you talk about the distribution strategy a little bit better. So stay tuned. We'll try and get some better examples of that for you. I don't know if this is going to run. Yeah, so it does run. But it does have a distribution strategy. And basically, it just it's just aware of the hardware configurations when it runs. And okay, so that was basically, that particular example is just kind of an overview of basically touched on everything that you would see, all the basic I/O stuff that you have to sort of be concerned with. The next one here is just the hello world. I can jump into that one. So now I just have a whole series of examples that I can walk through. So just raise your hand if you guys want to see this one. When I was doing this before, people didn't want to see this one. Then I went up going back to it. But anyway, if you've never seen an MNIST hello world, that you may as well take a look at it. But if not, we can just jump into the next one, which is the MNIST fashion one. So is that, what do you guys think? Yeah? How many people want to see hello world? Okay, how many people want me to jump into MNIST fashion? Okay, all right, so we'll skip hello world. I'm going to trick you. I'm going to make you look at it anyway, just because it's only like 10 lines. So let's see. Is this the beginner one? Yeah. I won't spin up the notebook. I just want you to see it so you can say you've seen it, just in case. So there's your data set. There's MNIST. They'll train it. There's your train the test set, and then there's your model. So just so we're all on the same page here, flattens out the 28 by 28, and then we've got the dense layer, we've got dropouts here, and then the 10 out, and then then you fit, and then you're done. So let's take a look at the basic class. Okay. So I think we've got TensorFlow running already on this.
Can I open up any existing notebook in this studio?
Yeah, you can import any IPython notebook into this and then just start running it. And then typically the free tier's got roughly the same resources as a Mac or something like that. The thing that's nice is you can have a few of them open and have a few of them running without having your Mac open. So it's kind of nice to have this available.
Will it time out?
It will time out. Well, what it'll do is it'll spin down, and then you can spin it back up. So yeah, if you're doing heavy training, make sure you checkpoint them and save the files and things like that, so that you don't have to reproduce the training part of the notebook. But when it spins back up, it's usually pretty quick. So. All right, so we'll go into let's make sure all this stuff is okay. So we got 2.0 alpha installed. We'll go ahead and import MNIST fashion set. That's just a figure. That is not the actual. I mean, it is the actual data set, but we don't use that image. So the Keras library has its own data sets. These are the classes here, 0 through 9. And to be honest, this is just a more interesting version of MNIST, right? It's got 10 classes, it's got a bunch of images, but the data is slightly more interesting. Still black and white, and so we'll put class names. And so there's some of these that I like the examples because it gives you a feel for the inputs and the outputs. So the next couple of examples tells you how to think about this data. And may or may not be obvious to some people. I found it very helpful. So just so you can, you load this images and okay, so there's 60,000. This is 60,000 images. There's a 28 by 28. Each image is 28 by 28, right? So this is how you get your head around what's happening with the data, and it's asking, maybe the obvious question: how many training samples are there, right? So now we're going to look at each one of those has. There's a Y variable called train labels. It's going to give you all the labels, and now you've got. Now your test images are going to be 10,000 samples, right? And then just some plotting functions here where you can actually take a look at the sneakers, and the image goes from 0 to 255 here. So we want that to go from 0 to 1. So that's all you do there. It is just scale by 255. This is not, it's surprising how low level some of the ETL is on TensorFlow. So coming from Spark, all this ETL has got methods for handling all this stuff, and you still have to go through this and treat it like NumPy arrays and kind of manually crunch through some of this stuff. So we'll go through some examples about one-hot encoding and all that kind of stuff. And you're still really having to kind of get in the weeds with the data. You're not using these high-level APIs to handle it. So that part, some of these examples kind of help shore up your thinking on some of that. Okay, so, and I mean, and everything that we're doing here is matplotlib. I think we use Seaborn and some other things like that. So you really do have to kind of know where the moving parts are of these things. So, okay, so here's the MNIST data. Now we've got the picture and the label, so we can kind of see what we're working with here. Go ahead and build the model. And this is a super simple model, right? Flatten it 28 by 28 and then 128 neurons in the one layer between. And let's see what we can compile the model. Now, I don't know why there is a categorical cross entropy and there's a sparse categorical cross entropy, and I don't know why one is favored over the other, particularly for this data set. So, so if anybody has any thoughts on that one, that'd be great. Okay, so then we can go ahead and train. Now, so, it's always model compile, and then model fit, right? This is the workflow. And usually, I mean, the idea is to get it to where you can, read this pretty readily. So this is just an extra bit that I added to figure out what the gadgets are that are running. It's got this XLA CPU that makes it run a little bit faster, but there's no GPU running on this machine quite yet. This one one more time. So now we can evaluate the accuracy. And there it is, 87%. Not great. Now we do predictions. So now some of these lines are just kind of nice because now you got test images and it's an array of images, outcomes of prediction, and an array of predictions, right? You don't have to write any for loops or anything like that. Here's the first prediction. So can you tell what this prediction is saying?
Last class?
Huh? The last class?
It's predicting the last classes.
Yeah. So it's 0.95 is the last element of the array. That's the largest one by far. Everything else is pretty much 0. This is kind of what you want, right? But at the end of the day, this is the output of the 10 neurons, right? Each neuron put out a floating point number, and if it's well behaved, one of those is going to have a peak. We'll see what it looks like, and then you can use this thing called argmax to find out which class it's predicting. And then if we go back to the class, it just maps back into a label.
There's some to one.
It doesn't necessarily have to sum to 1. No.
It's softmax, it will.
Huh?
It's softmax, it will essentially.
Is it softmax that's coming out? Where is it? Oh, okay. See how close it is. Those are what NP sum. NP dot sum. Is that right? Yeah, 1.0, look at that. Okay. Cool. So, yeah, good. So, there's another one, well, I'm thinking the one where it doesn't quite get it. Let's see if that one tells us something. So, okay, so then we do test labels, and that turns out to be, and I'm trying to remember, was it class names? predicted that it was an ankle boot. Okay, so here's some stuff where it's just a bunch of matplotlib stuff. But what it does is if it gets it right, it plots it in blue. If it gets it wrong, it's in red. And then I'll also plot the value array, so we got to see what this stuff looks like here. Okay. So it's an ankle boot and 95%. So here's one where it gets it wrong. Now, I'm kind of curious to see what the value is. I'm sure it still sums to 1. So, but there's definitely a second spike that appears. It turns out this other spike is actually what it's supposed to be. It just got it wrong. So, but 87% of the time it gets it right, and there's the one where it gets it wrong. I'm not sure what all this is. This stuff, the extra stuff here. So, let's see, we've been at this for about an hour. I want to make sure I cover the examples that you guys want to see. Let me just quickly go over the example, because I think we're going to, what's our timeline?
I think you're all right. Just reminding myself of the itinerary. We were talking about hopefully by sort of 10 to 5, we're kicking into QA.
Okay.
So, yeah,
Okay.
can you give 20, 30 minutes more sort of just presentation time?
Okay. Okay.
A little bit flexible?
Yeah. So I've got lots of examples here. I'll just very quickly kind of touch on the ones that I want to cover. Some of them have this really nitty-gritty code stuff where you get to see what the inner workings of the code and how the APIs work, and then some of them are just kind of higher level. So the next one is the text classification one. This one's pretty interesting. It builds up vocabularies and things like that. Feature columns. This is pretty handy to know. And the basic regression and save and restore models, and then the TensorFlow. So if you guys are ready to take a look at text classification, I'll just jump into that one. We'll walk through the examples. And then if I go through those, that'll probably get us make sure I've got all those, get everything covered in time. If it starts to look like we're going to run out of time, just start to raise your hand and say, hey, I really wanted to see save and restore. How could you make me miss out on that? So let's go through. We'll just jump into basic text classification. Can everybody hear me okay? I'm testing. Okay, so this one, text classification of movie reviews. Just make sure. If you notice, I'm always doing this TF-dub version in all of them, just because sometimes if you spin up the virtual machine, you can't remember what was installed and what wasn't installed, so you always kind of double check. There are a couple of versions of TensorFlow that you can install. There's TensorFlow, which will just pull down whatever the current GA release is, which is like 1 point something, 1.3, 1.4, something like that, and then you can download this nightly preview, which is really bleeding edge stuff, or you can just do the TF 2.0 dash alpha 0, and that's the one. That's the one that I've been working with mostly. So, but I think this one, I have to double check, this one maybe will play better with the TensorBoard API. So, okay. So there's the IMDb data set. Training entries. Okay. So this is the training data. This is the bag of words model. And what we've done here is we have trimmed it down to just the 10,000 most popular words in the data set. And then for every word, we've assigned the a word index to it. Right. So that this is the text in integer form. So that's just the first article or first review. So then now we have the word index here. So there's a lot of high-level stuff happening here, right? This is this get word index is coming out of the IMDb method. So pull that down, take a look at that. Now we'll just recover what this looks a little bit more human readable, and you'll see that it's not, the grammar's not perfect because we filtered out some of the words, right? And it doesn't matter because it's a backwards model. So does anybody know what kind of neural network would be good for sequences of words?
LSTMs?
LSTMs, RNNs, yeah.
GRUs?
GRUs, exactly. I do have an example with some RNN generating Shakespeare, but it takes about 30 minutes to train on my machine. So we can kind of walk through how to set it up if you want to do it. Okay, so then we prepare the data here. All we're doing is padding the data here. How many people are familiar with all this text processing stuff? You guys do this a lot? Yeah. Okay, so this is how you do it in TensorFlow. Again, not the most elegant APIs for this kind of stuff, to be honest. There's stuff out there that's a lot better. This is basically just Python, doing Python stuff with it. Something like Apache Spark has much more elegant APIs for processing and stuff. All right, and now we're building a sequential model. Now we're doing an embedding layer. Global average pooling is something that just connects to the embedding layer, and then it's connected to a dense network. So an embedding, how many people know what embedding is? Okay. So that's all that's being done here. So you'd have a very high dimensional sparse vector, which means you've got a vector with 10,000 elements. Only one of those elements is got a tick mark on it because that's what corresponds to the word. You want to represent that as sort of a dense vector of but you have to sort of pick the right dimension, so it's not a 10,000 dimensional vector, but it's not a 2-dimensional vector, right? So it's somewhere between, and so 16 seems to be a good size here, and so it's going to train the model and produce a word embedding, and that basically just takes that big sparse input and turns it into something denser, and then that gets just fed into the next layer of neural network.
So when you're doing this like embedding, or I saw before flatten, it's not technically is adding another neural layer, is it? It's just doing a data transform first?
Yeah, I mean it is kind of a neural network in and of itself in embedding, right? So it's actually so the input is 10,000 the input is 10,000 elements. The output is 16 elements, right?
Mm-hmm.
So it just basically takes that dense vector or it takes that sparse vector and turns it into a dense vector.
Mm-hmm. What about the flattened one? Was that
This average pooling? The flattened layer for image processing?
Yeah.
So the flattened one takes a 28 by 28 image, or in our case, it was 28 by 28, and unrolls it and turns it into a one-dimensional vector. All it does is just take 1 through 28,
Yeah.
and then the second row would be 29 through whatever, 29 to 20.
So that's not a layer of neurons that are getting weights, it's just a data transform?
That is just a transform,
Yeah.
That's just a, there's all kinds of fancy stuff for handling images.
It's just a reshape operation.
Yeah,
When
and
you-
but
Yeah.
we're doing it as a
don't
layer
find
in
it.
here, so you can get it like as a sort of a tensor that can be distributed efficiently using the TensorFlow backend. Is that
When you're doing an embedding or when you're doing a
the
flattening?
flatten? Like, yeah.
Yeah, flattening
Whatever
just
you're
because the way the neural network works, it takes a one-dimensional vector. It takes a vector as an input. And so if you have an image if you have an image, you just say, oh, that image is somehow a vector, right?
Sure, but putting it into Keras and letting TensorFlow itself handle that simple operation just means it can be done in a parallelized way. Is that why you're putting that in there rather than just doing it as a pre-step?
Oh, I see what
Data
you're saying.
transformation.
Yeah. That's a good question, right? Because so I think the question you're asking is, why is something like flatten part of a model? Because models should just be neurons, right, instead of all these operations, right? And I think that's a good point. I mean, you could imagine that there's a set of pre-processing that would take place. It goes into your thing that's just neurons, and then out comes some other stuff. And during the model part, it's just the neurons, right? 'Cause there's no training required in a flattening step, right? There's no optimization or anything. It's just a flattening step.
That's
And,
the difference between the model and the computational graph that is actually running to, update the model. And this is part of the computational graph, not so much of the model.
Right, that's correct. Yeah. So for example, the weights part of the model wouldn't have any information about the flatten or anything like that. There's other things that happen inside of models so if you get into things called convolutional neural nets, there's all kinds of things where they average out things around each pixel to get certain kinds of data points and all that. And that's also doesn't require any training, it's just a whole series of pre-processing steps.
And sometimes when you're working with convolutional neural networks, after the convolutional part, when you're going to connect that with the fully connected part, you have to flatten whatever that's coming from the convolutional maps. You have to flatten them so they can be input to the fully connected layers. So you find yourself using the flatten thing not only for in the beginning, like to pre-process the inputs, but also inside the architecture of the network.
Okay.
So yeah, I wonder that's probably a reshape, NumPy reshape that's working like.
On the back end.
Yeah, exactly.
Yeah.
Probably it's nothing that fancy.
Yeah. I mean, TensorFlow library at its core is just like an n-dimensional array library. It's an array for processing all of these arrays and dimensions and all this other kind of stuff. So all this, transpose and reshaping and all this other stuff is something that TensorFlow is designed to do. And so, yeah, when you write it in Keras, it just kind of talks to the TensorFlow API and does all that kind of stuff. But yeah, I think that's pretty much what this global averaging pooling is doing, right? It's just taking this output of this embedding and piping it into the dense layer. You'll see it in LSTMs too. The LSTM will come out. You'll put the layer into the LSTM, and the LSTM gets called multiple times to generate a time series. And then out will come a time series, and then you're like, okay, well, what do you do? How do you pipe this time series into a dense layer? So there's all these extra methods that allow you to kind of deal with time series in a way that is coherent with the dense neural networks. But yeah, so the embedding is, it's very handy to have. I mean, there's the famous embedding that you see a lot is this thing called word to vec. I'm sure that one's been trained on Wikipedia, and so that one's used a lot. That one you can just pull down and use, and you'll end up using that one. You see that one used, for example, in clustering or something like that, where the clustering algorithm is sort of what the focus is, but it turns out that it's using this really fancy neural network to pipe into a clustering algorithm, which has been around for a long time, but actually the use of a neural network has enabled this clustering algorithm. It's actually what's made it useful for text at least. So yeah, so there's some of that. Then we can compile it. So this one is, okay, so this is compared to categorical cross entropy, right? This is the binary cross entropy because now we're training on good or bad, right? The reviews are either good or bad in this case. So metrics of accuracy, and then again, you create a validation set. Now you're not even pulling these down randomly. You're just taking the first 10,000 entries and making that the validation set. So, or what? Is it the last 10,000? Yeah. So that.
Do you know if there's a Keras wrapper for using BERT for NLP classification?
No, I don't know that.
Okay. I think it came through from Google. It's just a new approach for NLP processing. I haven't looked into it too much, but I think it has a very, very big pool of like pre-training on grammar and language and maybe embeddings under the hood.
Okay, sure. Yeah, I definitely have to check it out. I know. I mean, a lot of this, things like Word to VEC are available on the TensorHub site that I was mentioning, and so let me put this one here. Oop, there's something here. Okay, so we've got a training loss and a validation loss. What do you think is the story that's emerging here with this plot? What's happening, do you think?
After the 25th epoch, probably starting to overfit.
Yeah, starting to overfit, and actually, not only is it overfitting, I mean, it's actually, validation is actually going up a little bit, which is, that's a little unusual to see, right? Sometimes it kind of flattens out, but that's actually, that's probably, I think out of all the examples, that's probably the most severe overfitting case that we've seen, because now this is really, this is actually causing it to perform worse on the validation set. This is why later on we'll show you what the Keras callbacks will do. So this will callbacks will allow you to filter on that. You're technically not supposed to use your knowledge about validation data to make decisions about your fitting procedure, but if you use a callback, you can say, if this validation score is not changing, you can stop the fitting.
So is it a version of early stopping?
Which one?
Callback? Is it a version of early stopping?
Yeah, it's an early stopping. Okay, so here's the accuracy. It's leveling off, and I can't even tell if it's dipping down if we use the accuracy measure. So so that's the text modeling one. I wonder if there is some other. Let's jump into.
Is there a way to convert this model from TensorFlow to PyTorch or PyTorch model and do TensorFlow?
Yeah, I mean, probably the file formats that are most transferable are the Keras format, So TensorFlow has its own format called it's a .pb extension. It's a protobuf format. It's usually people don't save it in that format unless it's got a bunch of really quirky TensorFlow stuff in it. So yeah, Keras models I think will import into all of those. Keras is actually just a spec for defining neural networks, and so all the frameworks will write some library to adhere to that spec. So I think PyTorch, Cafe, they all use Keras APIs in some way or another. So that's probably your best bet, is to say it's a Keras model. The Onyx format, there's the Onyx is a pretty good format for if you want to use the Onyx runtime, but you know, Cafe and PyTorch, they all support the Onyx format as well. So, but probably your best bet to start with is just Keras if you can.
And is there any way when we have, you know, model is deployed on the production, we would like to process a batch, a sample through the production system? So is there a way to, you know, make it parallel and ask the model to tell that, okay, hey, I have 16 GPUs, so that model will run parallelly on the 16 different GPUs? I mean, in TensorFlow 2.0 features, in any features have you?
Yeah. So well, I'll probably be able to answer that question better when I get that system running, because we're going to try. I need to get a GPU cluster so I can see how that stuff works. But I mean, it depends on the system that you want to set up, right? So usually, you know, training and serving. Training is usually like an overnight thing. Serving is very fast. So you don't necessarily need to dynamically allocate resources for training versus serving, right? You can have pretty lightweight serving machinery and then have some dedicated thing happening for training. So it's even, I mean, you don't really need GPUs even to serve the model. So you can just kind of upload it. But I think it depends on the case. So yeah, if you have more questions on that, just let me know if I answered your question specifically. Yeah. But yeah, I mean these. I think there's a lot of interesting things about getting these into production. There are, if you want, you know, fast serving, there are a variety of options that we really won't cover. Most of this is all notebook stuff, but there are a variety of options for fast serving. There are things like the Onyx runtime and other things like that, where it just takes the model, just as a runtime, and then it just serves the model based on inputs and outputs. There's other things. There's this thing called TensorFlow.js, which runs completely in the browser, and it's very fast. It runs on, you know, because it's tuned to every conceivable hardware configuration because it leverages all the browser optimizations. So TensorFlow.js is very fast on systems that don't have fancy NVIDIA cards, right? And then there's another thing called TensorFlow Lite, which is a serving framework designed to be running on, you know, Raspberry Pis and all. Google has a little version of this on their TPUs that they designed it for. So that's a good one for fast serving. I think that there is another service framework that I'm not as familiar with. I have to get back to you. But yeah, I mean, you know, probably the way you do it is you have some kind of Kubernetes things where you're deploying a bunch of pods that have a bunch of server frameworks, and you provide as much. That's how we do it, right? All the Max models are all. I think it's Flask. Everything's wrapped up in Flask. It just serves it in Flask. That's one way to do it. And coordinate all that with Kubernetes. But yeah, okay, so we can jump into feature columns real quick. This is kind of getting into the text. So many people are doing text processing, this kind of NLP stuff. Okay, so just kind of show you what moving parts look like in TensorFlow. Again, I was kind of surprised when I got into this. That the API hadn't come along more on this. But I mean, it just kind of points to what this was designed to do. It's a computation engine for training neural networks. And then it happens to have a very nice API called Python that has all this stuff built in, pandas and scikit-learn and stuff. But really, you know, it wasn't addressed. The text processing machinery was not really addressed specifically, I think, as part of the development philosophy. Okay, so scikit-learn, everybody familiar with scikit-learn? Make sure we get the right version. Don't. So the reason I have to reinstall some of this in some places and don't have to reinstall it in some other places is that Watson Studio offers this thing called an environment. And that could be one of many different things. So I have a Python 3.5 environment, I have another environment that has a GPU, I have another environment that has a Spark cluster. So if you look at this kernel over here, it'll have this environment option. You have all these different types of environments. So you can get your, it'll manage your versioning. I can run R. I can run. We're still working on getting the Teslas up and running. Okay, so we gotta install this thing. Oh, I think we had to restart the kernel. So when you pip install, you have to restart your kernel to get the libraries to take. Go back, just make sure all this stuff is working. So just a heads up, there's a lot of clunkiness if you're actually running these notebooks with the pip install stuff. Make sure they're got commented on. Go back in business. Okay, so this is leveraging a lot of the pandas stuff. So now you can see, anytime you see these fancy tables, you're using pandas. This is using this dataset API again. TF data set from tensor slices. So let's make sure I can get to the point that I wanted to. Okay, so then we've got here's the feature column, and then there's the this is all the bucketized. This is the bucketized kind of thing where you take all the ages and then if it's, I think it was, the age was 52, so it puts it in the 52 bucket. It's just like just a manual way of hot encoding or bucketizing your data. Categorical columns will do the same kind of thing. So now you've got this one here. This is actually an embedding. It's called, it's actually called an embedding method as part of the method here. So this is a slightly different embedding. And hashed feature columns, cross feature columns. There's only a couple of things I wanted to show in this particular one. I'm going to create a dense feature layer. That's pretty much all I wanted to show in that one, was just some of the feature columns, how to use the embeddings. So let's jump into the next one. Okay, we can do a basic regression, so you can see what that one looks like. So this particular runtime, if you look, it had 2 CPUs, 8 gigabytes of RAM. And I don't think it's currently configured to use both of them. So how many people have used Seaborn before? Have you seen this one? There. Many people are familiar with this data set, the MPG data set. It's actually a pretty cool data set. It's got kind of traces the the inefficiency of the American cars until the Japanese came on the scene and started making efficient cars, and they were kind of change their tune. But what's interesting about it is you can get a long ways into this data set without really jumping into the deeper part of it. So, okay, so we're just doing some cleaning here. And I think this is all Panda stuff. So dropping NAs. Now this is a really funky way to do one-hot encoding, but that's the way they do it. See what they did there? This origin equals 3 times 1, and then put it into the. And this is I mean, you can tell this is. This is small data because you're creating a column on the fly, right? I mean, you can't really do that at scale. This is why, I guess, at some point it would be nice to connect the ETL. If you're using something like Apache Spark, it'll do all this ETL a lot more efficient, things like that. So, but this has got a data splitter. This is a cool plot. But what's interesting is most of this looks pretty much like normal machine learning. I mean, there's not a whole lot different happening here in terms of the way you're analyzing data, the way you're understanding data. Even in the text processing part, right? It's feeding it into a neural network, but you're processing it the same way you would if you were just using machine learning. So this is the pair plot. You guys seen this one before in Seaborn? So on the diagonals are the distribution of the values, and then every off diagonal is just each variable versus each other variable. This one, it has the value here. It should have, histogram points here, but they just keep putting the value here because this is the way they plot the axes and everything else. So yeah, so you can see that MPG displacement is MPG versus number of cylinders. Let's see. So MPG is high for 4 cylinders, and it goes low for higher number of cylinders, and kind of makes sense. Okay, now we're actually doing some feature engineering. It's probably a better idea to do a little bit of feature engineering on regression, just because you're really pushing on the floating point side of things, right, rather than doing categorization. So this is subtracting off the mean, dividing by the standard deviation, and we're going to build our model here. So do you see what's happening in this model? Anything surprising? Anything would you expect it to look like this for a regression? it's got a single floating point number as an output, but it is a deep network. Right? It's not a linear regression. It's not a. This is a it's got 2 dense layers. ReLU activation. So this is, and so it's possible to take these networks and have the output be a variety of neurons too, and have those also be interpreted. So the ones that I'm actually getting more and more interested in are the time series ones, where you have the output is an arbitrary number of neurons with the time series associated with those neurons. So you can have a multivariate time series predictor. We have a whole series, an arbitrary number of time series that go in, an arbitrary number of time series that go out, and you have a completely generalizable time series predictor for markets, for weather, for a whole variety of things. So that that sort of assumes that floating point numbers and regressions are well predicted with neural networks, and I think that's still somewhat of an open question. But so we build the model, and we take a look at the summary here. Train the model, see how fast this one goes. Oh, this one goes pretty fast. Okay. So we're doing 1,000 epochs here, and you're just printing a dot instead of all that other stuff every time I hit an epoch, and it's going fast. This one actually is pretty sensitive to the hardware sometimes, so sometimes this doesn't go quite as fast. And are we done? Yes, we're done. Okay. So here's our 1,000 epochs training error and validation error. And what are we seeing here? I think we've already kind of thought about this a little bit before. So this is again maybe some overfitting happening, and this one actually looks like it's leveling off a little bit, but maybe it's scooting up a little bit. It's kind of hard to tell. If I did grid on, I guess I can figure that out. So that's 1,000 epochs. So I think somebody has already been exposed to this early stopping method here. This is part of the callbacks, and this will compare validation loss. So patience is 10, so that means that after about 10 steps of this of no improvement, it will stop the training, which takes it from 1,000 epochs to about 50.
So you define that there should be 10 epochs.
Huh?
So you define the number 10.
Yes.
Mentioning that it should not change.
If it doesn't
over 10
improve
epochs.
after 10 epochs, yeah.
So you only set which variable to monitor.
Yeah.
It's easy.
So it's handy. I mean, it's definitely handy. If you know that about your data, you know what to look for. It's pretty nice.
Is that new in
It's
TensorFlow too?
I think that's new. Yeah, I think all the callbacks are new. And it's pretty handy. Yeah, it's pretty handy.
You write a lot of code. And
Yeah.
I mean,
You can
for
spend a lot of time figuring it out.
Yeah, and it was even harder before because it was running on the GPU, and it's like, this whole idea of a session was like, it's like you train your thing and you let it go in the wild on the GPU, and you have to kind of wait for it to run to get the information back. It felt so even any kind of inline monitoring or any kind of reactive programming is pretty hard. So this kind of stuff is pretty handy.
So we should probably kick into Q&A if you'd like to leave some dedicated time for it.
Sure. Yeah, I mean, just walking through this, make predictions. I think I have some stuff on save and restore models, and then I've got a few examples that I can walk through if you want to see them, or just any kind of open questions. Really, just let me know what works out for you guys.
Do you, what's your preferred approach for like parameter searching with TensorFlow?
Parameter search, oh, like a grid of hyperparameters or something like that?
Or maybe even bringing in different approaches to data preparation into that loop. I was wondering whether the class approach you mentioned earlier could help facilitate that in a parallelized way. I don't know.
Yeah, that's a good question. There are other, so they're releasing a whole suite of pipelining tools around TensorFlow. They're slowly trickling things out to help process, and I think a lot of that stuff will have wrappers that will allow you to do things like that. So from coming from the Apache Spark world, they had this API called ML Pipelines, which allows you to do that, basically create a grid of hyperparameters around your model and then search, and it would just search through everything automatically, give you all the metrics. I suspect that the APIs, all the stuff that's coming out from Google will have some of that machinery and yeah, probably do it in parallel in pretty clever ways. But right now, this is the kind of stuff that you're doing. You're basically, you're packaging. Basically, you're still packaging. You're packaging a piece of code to run on a piece of hardware, right? That's still what it feels like when you're running it. And it's a lot cleaner and a lot more elegant and a lot more interactive with the hardware, but that's kind of, but neural networks don't require, it depends on how you view neural networks. The idea behind neural networks is you don't necessarily have to do all that extra feature engineering that you have to do for machine learning. The hyperparameter searches are not as difficult. They're generally more robust, so if you have a neural network, the idea is if you have one neural network with in parameters, you make a larger neural network, you wouldn't expect that larger neural network to be better or to train faster, but it turns out it does. So it will actually convert, a larger neural network can converge faster than a smaller neural network because the parameter space is easier to navigate. It's sort of like it doesn't get stuck in local minimum. It's got like a lot of parameter space to kind of move around and find a better solution. And if you do the regularization properly, it won't overfit. So the regularization that happens in neural networks is this almost, really the only way you can regularize in neural networks is to do the dropout layer. And there's kind of like a general thought that somewhere between 0.15 and 0.3 is a good dropout rate for that. And so really there's really maybe one or two hyperparameters in the dropout space that you want to tune, and then a lot of the other stuff with the feature space and things like that. The hope is that the optimizer will capture a lot of that. So it's not as critical as it is in the machine learning space, where you really have to get your features just right. You have to, the feature engineering side of it is actually pretty hard. The idea behind the neural networks is that feature engineering is a little bit lighter task, and you just throw lots of computational power on it.
Okay, thank you. Yeah, should we grab some questions from the floor? And then perhaps just for lack of a mic, could you perhaps just repeat the question into the mic? That would be, because we don't have a second one anymore. Sorry.
I don't even know if you guys could hear me.
Oh no, it was good. Yeah.
Okay.
When you say model for the carrots, you mentioned it's still the database platform and whatever. Before I was trying to mix like carrots with TensorFlow functions together, and then I had trouble saving in just pure carrots format. So I had to use checkpoint, and then I could save and load it, and then it seems like in 2.0 it's still the same. So like and then you also mentioned you can create your own class to extend layer, and then
I assume you can make some TensorFlow functions. Does it have any utility or thing to actually support saving in one format? Like can I mix Keras and TensorFlow and still just hold the saving function of Keras? That's what I'm asking.
Yeah, so I mean, again, Keras is a spec for defining models, right? So if you're using something that's outside of that spec, then Keras won't be able to save it. So yeah, so as soon as you start getting coloring outside of the lines and having to go into TensorFlow, then you just save it as a TensorFlow model, and then you'll be able to import and export it that way. But sometimes it's just a few tweaks that you might need to make it savable as a Keras model. So I don't know if you can do it. I have to check, but there may be a way to save the TensorFlow model as a JSON object or something like that, or have it somehow viewable. So we've been wrangling back and forth between Keras models and Onyx models, and that's why looking at those JSON files or the YAML files, you can see a little bit more what's happening with the layers, and sometimes it's just simple stuff like the random the kernel initializer is using a different random number generator or something weird, so you might be able to fiddle with it that way to recover the format that you want. But the TensorFlow's flexibility is nice, but then as soon as you start using it, then you can't, all the transferability disrupted.
Would you be aware if there's any performance upgrade to the into TensorFlow 2.0 over?
Oh yeah, at least 2x. Even without GPUs, it's about 2 times faster. So yeah. Just doing these examples would take twice as long in TensorFlow. So I'm not sure exactly how they got it because it was already running pretty fast. And so it's some pretty impressive improvements for a 2.0 code base.
Is there some performance impact so when you use the eager mode in TensorFlow 2, is it it's going to run not as fast as the static mode, or kind of the same?
When you run the model itself, it runs on the GPU, and then you're still getting the same performance. The only thing that you're getting really is you can run little snippets of code and immediately inspect the variables. So you don't really see a performance hit by using eager execution. Yeah, that's a good question. Yeah, because and I haven't really used it as much. I haven't really used eager execution because actually I've gotten to the point where I'm using Keras API so much more now because it's just gotten so easy to write code. But yeah, if you want to write TensorFlow code, that's definitely the development cycle is like 10 times faster by being able to do eager execution. That whole sess.run thing is just crazy. Because that's the kind of thing that you would do if you're running code on a cluster or something, right? Like launch a job and wait for the job to return a result, but it's like your GPU is right there and you're doing the sess.run.
Yeah. Now, are you able to join us for refreshment? To be hanging around a bit?
Sure, yeah.
Some more questions?
If you guys want to take a look at these other examples, I can walk through them. I mean, after the break, I'll just do a quick plug. Let me just do a quick plug for a couple things, and then I definitely want to talk about call for code. I just want to do a quick blurb for call for code, and then
Please,
wrap
yeah.
up. So I got a couple of these examples. These are also in the notebook. I got a deep dream example. If you guys want to take a look at that one. Also, I think somebody was asking about a TensorBoard example. I have one of those in there. If you guys want to, just grab me and I'll show you what that one looks like. What this one will do is render TensorBoard in the notebook. So it's actually pretty.
So that's possible now, right?
This is possible in Jupyter Notebook. It's not quite there in Watson Studio, but you can do it in Jupyter Notebook. But you got to get the versions right. I'll show you how to. You got to install each version exactly right, or else it's still kind of. Yeah, it'll take a little while before it's disentangled, but very cool. I mean, it really puts everything in one page, and yeah, it's pretty cool. And then we got a neural style transfer example we can walk you through, and that's pretty much it. I just want to, Eunice talked about call for code. We just had the winner from last year at Think in Sydney speak, and he did a thing called Project Owl, which was this like ad hoc wireless network for disaster preparedness. It was really, really cool. So you can rapidly create wireless networks in places that where all communications went, and really useful. And then after winning that prize, you actually get a team of IBMers that will help implement this in places. And it's got a $200,000 cash prize too. So it's definitely worth checking out. I mean, it's something we're really proud of. It's got a lot of really great people behind it. So, but yeah, if you guys have questions about the examples, the remaining examples, just come grab me. And thanks so much for coming out. We really appreciate it.
Thank you so much, Jerry. I'm really looking forward to trying out some of those new API features, and I'm going to try out that IBM notebook feature too. I'm looking forward to not having my CPU crunching while I'm doing other things while I wait for my models to train. So, yeah, that's awesome. Thanks again. And there's going to be pizza and beer out there. And let's once again thank IBM for having us and for providing that.